And the last piece of information, this guy has a high input impedance, and that is going to lead us to another concept, which we are going to talk down here, is a voltage follower or an input impedance buffer. And this is a special case of inverting, non-inverting amp, where RF is 0 and RS is infinite. So this guy here is the non-inverting amplifier, right? For a non-inverting amplifier, we had this RS and we have this RF, right? This would be a non-inverting amplifier, same as this guy, right? It has a resistor, and a source goes into the positive. And what if we just get rid of this guy, just go away? The way you kill this thing is what? By making this as an infinite value, right? That's just disconnecting this thing, right? Super large resistance is like disconnected wires. And by making this resistor RF to 0, then that's just a wire, right? So what we just did was, from this non-inverting, we made these values like that, and it pulls down to this thing. Okay? And what happens to, but still, because it's a subset of this non-inverting amplifier still, it may follow this kind of rule. So V out, assume this guy goes to 0, this guy goes to infinite, right? Then what's happening? That's just Vs, right? So this circuit is nothing but doing, you have your source signal, and then it's just passing it out to your output. If you have 1 volt sign, it's going to have 1 volt sign coming out. It's not amplified or it's not shrunk down. It's just same passing it. So it's called the follower. All right? But why would we need that, right? You can just have it as is. Why do you need like additional stuff that does nothing to it, right? Because there's no change in your output. It's just passing it. All right? So let me just write this thing down first. Probably it's not going to explain the meaning to you, and then I'll use an example to kind of illustrate what the meaning is. All right? So the reason is we would like to provide high input impedance, okay? So that very little current is drawn from the source. So the power of source is not affected. And most of the source voltage transfers to the load. So Vs is going to be VL. This is the reason why we're using this kind of nonsense thing. Okay? But I'm pretty sure you're saying, hey, what are you talking about? Okay, so let's try an example to see what's going to happen if we use this and if we don't use it. All right? So let's focus on this case. This here is some sort of sensor we are using. Okay, we just bought a sensor, maybe a thermocouple, I don't know, whatever sensor. Generally, sensor generates some voltage, and we were measuring voltage, right? And it's going to have a small voltage source, and it's going to have some parasitic resistance in there. Okay, and then when you measure something, you want to measure voltage out of something. And in order to measure voltage, you need to have a resistor. That way, the current flows across it, and then you can measure the voltage, right? So you have a low voltage resistor like that. And what if the sensor you've got has a very, very large parasitic resistance. Okay? There can be some cases like that. And your load resistance is much smaller than that value. And let's try an example. So RS was 100K, and load is 100 ohm. Let's just assume like that. In that case, most of the voltage is going to be on the source resistor, not on the load, because the load is going to be RL over RS plus RL times VS, and that is going to be 0.001 VS. If we had two resistors like this, but it's just nothing but a circuit like what you see I highlighted, right? So some voltage is going to be applied here, some voltage is going to be applied there, and the sum is going to be VS, right? And if this resistor is very large, all of the voltage is going to be applied here, and we have tiny voltage applied there. So based on this equation, your output voltage across this point is 0.001 times your source voltage. So say you are measuring a thermocouple, and it generates naturally like tiny voltage. And that tiny voltage is not being measured by your system because that is all applied to this guy, which is a parasitic resistance. And what all the juices spoil here, and you cannot measure anything out of your measurement node. See what I'm saying? So ideally, you would like to have your source voltage same as your load voltage. That way, all your voltage is passed to your load. That way you can measure it. Say this is 5 volt, you would like to measure 5 volt out of it, right? So that's the reason why this is not a good case. However, if we add a voltage follower like this, okay, so still this is 100K and this is 100 ohm, and we are adding a voltage follower. The voltage here, Vs, is going to be same as voltage here, Vout, just like what we had here, right? And if we do this thing one more time, Vs, VL is going to be Rs plus RL times Vs. And because our load is going to be having additional very large impedance that is added by this Opamp, now it's not anymore 100, but it's 100 ohm plus very large resistance. So this is super large, this is super large, they go away, and this is similar to Vs. You see? That's the reason why sometimes you want to have a voltage follower in between some sources. It's like kind of blocking the energy consumption qualitatively speaking, I would say. So instead of burning all your energy at this parasitic resistor, it is passing that information to your load where you are actually measuring. All right. So it may look like, oh, it's not doing anything. Hey, your output is same as your input. Why do we need this? In some cases, we would like to have this because it kind of disconnects between your source and your load. That way, all the things are going to be applied to this guy. Okay? So after you understand this part, if you go back, probably it's going to make sense. So provide high impedance input impedance. So very little current is drawn on the source. The power of source is not affected. It's not being affected. And all the source power is transferred to the load. So Vs is going to be Vi.